about chi-square from bio. What I would like to emphasize here is that you do not call it chi or chai. It is not a T. It is not whatever in martial art. It is not any of those things. It's called chi. Chi-square. Okay, and chi is a letter. It's a big fancy X, which we're going to write in a few minutes. If you could just try not to say all the other things just to get under my skin, that would be all. Okay, chi-square test of goodness of fit is a test. So when you see test, that's exactly what you think it is. For comparing more than two proportions to a hypothetical claim. Okay, I want you guys to think of this like a 2-sample test for proportions, except for it's like a 3-sample or a 4-sample, or a 5-sample or a 6-sample test for proportion. And anything sample, anything above 2. And there are 2 things you need to know. The data must be categorical. And we're going to work in a list that must have counts, like whole number counts. And what I want you to put here is L1. Most of chapter 12, this first part of chapter 12 is really, really calculator. It's mostly all calculator, which is great. There are no confidence intervals in this chapter either. That's all hypothesis test. So you don't have to remember anything about intervals. It cuts everything in half. So this is again going to be mostly on the calculator and no intervals to worry about. Everything is simple, which is wonderful. Okay, anyway. One weird thing is that the null and alternative hypotheses are sentences. And basically you're just going to say whatever the question is asking. So these guys are seniors, actually. I just want to let you know that information. They're seniors in high school. This table, all of them, they're seniors.
I'm really impressed.
Mm-hmm. What? It's still statistic, no. No, there's an applet. Okay, so what it is, there's a computer applet from the New York Times that, if you play rock, paper, scissors with it, and it over time can predict what you're gonna say.
Oh.
Yes, it's pretty good. I have them over here. Did I not give you a packet either? No, I can be part of it. No worries. Here you go. Okay. So null hypothesis, alternative hypothesis are sentences, basically. It's the same as what the claim is. It's different from what the claim is. And then alpha. Okay, this is how you write the plan. This is chi right here. Big fancy X looking guy. Chi squared. Test. Of goodness of fit. Okay. How do you think that you meet the random condition here? Yeah, look for the word random in the problem. I know, it's shocking. 10%? I think you guys could all do 10% conditions with your eyes closed. Okay, however, large counts is different. I know. Walter has nothing.
Oh.
Yeah, that's not true.
You don't have T problems or T test?
No, he has a team test.
Check like last week.
No, I didn't say that anything about the team test. I just thought you did the T problems, Art.
No T problems.
You have an older brother?
Yeah, two older brothers.
Yeah, I know the last.
Oh,
Yeah,
checks out.
I think I went to school with one of them.
Okay, guys.
Oh,
Okay,
yeah.
so you
It's
guys
my
don't know what
math class.
expected counts are, you have no idea.
I don't know about,
I'm so sorry.
I'm
Get in
gonna tell you
seventh
how to
grade.
calculate them. It's gonna be multiple ways. Okay. I love you. Okay, so what are expected counts? Okay, now who from bio has the chi-square formula memorized?
I don't have that number.
Nobody? Somebody said it to me last week. You did.
I think I saw it.
Oh, on the yellow sheet, maybe. Uh-huh. Okay. Next question. Do you guys all know what the big sigma means? Sum. Nice job. It means add them all up. Okay, now we're gonna talk about what does chi-square look like. It's got its own kind of unique graph. The best part about it is that the whole thing is positive. There's no like negative infinity to worry about or which direction it goes in. It's always up. So there's no interval and there's no negative. There isn't one. It's great. I love chi-square. Okay, but I'm gonna give you a minute to draw this dealio. Yeah. So, actually, I have a couple things for you about that. First, no, it's a valid question. I have a tree diagram, not a tree diagram, a flow chart. That I made with boxes and arrows that help you decide what inference method to use. I'm gonna give it to you as soon as we're done with this stuff so that you can use it to help. And then I have a sheet of just situations where you just go through and figure out which test or interval it is. And we're gonna practice that. The very first thing we're gonna do to study for the AP exam is to do last year's AP exam. So we're going to try to find those keywords and things, because that is valid. And then we're gonna do the year before's AP exam. And then we're probably gonna do the year before that's AP exam. Both. Actually, that's kind of a false statement. I have the FRQs, but then I have the released MCQs, which are not, they don't release them every year. They only release every few years. So I have a couple of the previous ones. But I don't know exactly what year they're from. Does that make sense?
Yeah.
Okay. All right. So do you guys remember what degrees of freedom is? What minus one? Yes. N minus one. Okay. And do you remember what happened with the T distribution as the degrees of freedom increased? All those things. Yes. Perfect. Okay. Great job. This actually does the same thing. Okay. When you have degrees of freedom of 1, so go ahead and draw this as best you can. Degrees of freedom of 1 is something that looks kind of exponential. Okay, this is not your normal chi-square distribution. You would really never have a sample size of 2 anyway. Yeah, so this is just weird. But we're going to use the mean, mode, and the shape to help us determine how to draw them for the rest. So the mean is the degrees of freedom. But these are going to be skewed. So remember, that's going to be pulled into the tail. What we actually need is the mode, which is degrees of freedom minus 2. And that's only for degrees of freedom that are greater than 2. Otherwise, they look like this dumb exponential thing. If the degrees of freedom is less than or equal to 2, then it looks exponentialish. I think I just came up with that word. It's not a real word. There's no word as exponentialish. That's not a word, but you know. Yeah. Okay. But if the degrees of freedom are greater than 2, then it's right skewed every time. And the higher the degrees of freedom, the more normal. Okay, so we're gonna start to draw. I'm gonna get a different color. We're gonna do a degrees of freedom of 4. My degrees of freedom of 4 is going to be in red. Okay, you guys with me? Okay, so the peak of the graph is going to be at degrees of freedom -2. So what's 4 minus 2? Right. So that means the top of my graph, I'm just going to say it's here, has to be at 2. So I'm going to go like this. I'm going to go E. Woo. Okay, now we're going to do degrees of freedom 8. The mode will be 8 minus 2, which is 6, and make the peak lower. You guys see how the light blue one is more normal? Also, is your graph beautiful? Oh, goodness sakes, no. We'll probably only draw it like in the team test or. No, we're gonna do this on the calculator. It's mostly in the calculator. There's some stuff that you're gonna have to write, but most of it's in the calculator. So this graph, probably, I don't know, if in the homework, they'll ask you to draw it once or twice. And you'll probably have to draw it on the team test, because you know me, I'm a jerk that way, but this is really just for you to understand. But my question was, in the conclude, is there anything in there that is not as you would expect? So since our p-value of blank less than, greater than, we reject, reject. We do not have convincing evidence that the, and then answer the original question, the original how. Does that make sense? So that should follow your usual. The only thing that's really different about this is kind of the mechanics, which are just lovingly all on the calculator. I like. Okay, now flip the page over when you're ready, if you are at the end of the page like I am. And then you have cut and paste after this.
And I cannot remember the last of it. I'm trying to remember. I can sure try.
I told Archie your Arizona's going. Yeah. It was great.
Here.
No, you're not doing
Like you answered it, and I was like, is that check? And then I was like, oh. And you're like, oh, Seth, I'm about to go on an AI.
I want to know.
I'll name my-
Somehow they make me feel old.
No, I'm really not.
No, bad idea.
Okay.
But I can.
True, true that. They're not bad. It's
When
just
would
they're
you want to use the bathroom?
teacher locked. Locked? No, never.
Used to be. I gotta give up
That's
my
when-
email address and a photo ID. Once I'm in here, I can just go in the lounge. I want.
Do you want my
shawarma
key?
still Really
You
bad.
want my keys just in case?
Sure, peace of mind. I feel important. Still really want shawarma. Haven't gotten it yet. Hello.
Oh, hey. What factory is it? Jordan. Okay, I'm sorry, your class,
That's it.
your class is just gonna have to.
No more? Write it down. Write the whole thing.
why would I have to provide you more because your table is immature?
Oh, maybe you got one of us? That was such a good one. I can't. You asked for it.
Okay. Example, M&M's produced at the Cleveland factory have the following distribution of color. 20% blue, this is real, by the way, I looked it up. 20% orange, 20% green, 20% yellow, 10% red, 10% brown. Joey bought a large bag, found 14 blue, 19 orange, 15 green, 5 red, and 8 brown. State appropriate hypotheses for testing the company's claim about the color distribution in Joey's bag. Okay. The distribution of M&M's color is the same as the company's claim. Remember, null hypothesis. Nothing interesting is happening. Just like it should be. Okay, did they give us an alpha? No, so what do we use? Okay, we got that down. All right, so do the null hypothesis and alternative hypothesis make sense?
Yeah.
Just first, the distribution is the same. Distribution is different. That's it. No, we're thinking just the same. It's different. Calculate the expected counts and confirm that they meet the large counts condition. Okay, so how many candies did Joey get in his bag?
Uh,
13, 28, 28 plus 33. I'm missing something. I'm missing yellow. Oh, cripes. Yeah, sorry about that. I have a typo. I knew this was actually surprised that this doesn't happen more often. Okay, so total 65 candies. And I typed this like the win bullseye. So, okay, so to get the expected counts, what you do is you take it's kind of like n times p. So you take your total and then blue is 20%, so times 0.2. So we expect 20% of the 65 to be blue. We expect 20% of the 65 to be orange. We expect 20% of the 65 to be green. We expect 20% of the 65 to be yellow. I did that backwards, but it really wouldn't matter because we expect 10% of the 65 to be red and 10% of the 65 to be brown. Okay, so this is 13, 13, 13, 13, 6.5, 6.5. Okay, calculate the expected counts and confirm they meet the large counts condition. They have to all be greater than or equal to 5. Okay, you guys with me on the expected count? We just take the total times whatever proportion is assigned to that category. And when you add them up, you should get 65 again. Okay, now we're gonna do chi-square by hand. And we're not gonna do chi-square by hand the whole chapter. We're just gonna do it by hand today because I really need you to understand what's happening. And so we're going to go observed minus expected squared over expected. We're going to start with the blue category. And there are 14 observed in his bag. So observed minus expected squared over expected. Plus. Okay, how many orange ones were in his bag? 9. Observed minus expected squared over expected. Plus, how many green ones were in his bag? 14 that I screwed up writing. Okay, and will you guys trust me to do this on my calculator? Okay, so that comes out to be 2.385. That's not weird because we get Z scores and T scores, and they're right about the 1 to 2 range, right?
Yeah.
Okay, now we're going to do chi-square CDF. Okay, and it's our first time. I know, I'm gonna do it overnight. It's been doing that all day. It's driving me crazy. Okay, what?
Oh.
Okay, chi-square CDF is down here. So there's your normal PDF, CDF, inverse norm, inverse T, T CDF, and then your chi-square stuff is down here. Lower, upper degrees of freedom. The lower is always our chi-square value because these are always positive. So 2.385. Upper is always positive infinity. On these, you don't ever have to think about negatives and positives. This is always going to be a positive number because you're squaring them all. And degrees of freedom is 565. So 2.385. Degrees of freedom is number of categories minus 1. You might think that this is a weird p-value, but it's not. It's just a really common sample. He got a very common bag of M&Ms that he purchased. Okay, now this is going to be fun. You saw it. Okay. All right. Over. No. I just wrote the right thing. Okay, assuming. Oh, it's doing Star Wars again. You know what I mean by that? Like at the beginning of the movie, it does the land galaxy far, far away, and it like tilts up. It's
Yeah.
going back. Okay. Assuming the null hypothesis is true, what's next? assuming the null hypothesis is true. Mm, okay, so this is the whole reason we're doing this right now. These are written a little bit different. You're not going to talk about a sample mean or a sample proportion in this problem. What you're going to talk about is your chi-square statistic. And because they're all positive, it's always or more. Okay, what's next? Just by chance. Last thing, in a what is it? You can do it. Random. Okay. Really, really big p-value. Failed to reject. What do we say? Perfect. Of what? Okay, finish this up and I'll find your daily joke. Now we have 5 notes days left of the school year. 1 down, 5 to go. One of them's going to be after spring break. But guess who finished all the rest of the notebook setups today? Oh, it was me. There it is. Did you see my joke?
Yeah.